A proposition is a statement whose truth value can be determined as true or false. Okay. So, for example, the professor is very handsome. That will be not a proposition because for some people it might be true, like me. Other people it might not be, right? Okay. So, on the other hand, the something like grass is green, probably true, right? Or there are more people living in Antarctica than United States. That's definitely false. Those will be propositions. Okay. So if I have two propositions P and Q, we want to think about more complicated statements you can get from these things. And for example, if you have two statements P and Q, you can do P and Q, right? So this is P and Q. And from now on, I'll just be very abstract. What's the beauty of math? Once you make something abstract that strips out all the irrelevant parts so that you can get to the core of what's being discussed, okay? So for me, we don't really care what the exact statement P is, what statement Q is. It's just that P could be something that's true or false, Q is something that's true or false, okay? And in those cases, what happens to the statement P and Q? That's what we want to know, right? And to talk about this statement P and Q, we can build something called the truth table. Where you write down all the possibilities of P and Q, and then you write down the possibility of the statement that you put together as P and Q. Okay? All right, so what could happen? Well, it could be that both P and Q are true. It could also be that P is true while Q is a false statement, false proposition. And it could be that P is false and Q is true. And then it could be that they're both false. And because propositions are either T or F, there's no other possibility. These are the all possible ways that you could have P and Q. It could be they're both true, both false, or one of them true. It could be like P is true or Q is false, and vice versa. Okay, in that case, what happens to P and Q? If P and Q are both true, then we know that P and Q is true. Right? How about this? If P is true but Q is false, can you say P and Q? False. It will be false. Right? Same thing here. In other words, if any one of P or Q is false, then you can't say they're both true. Right? That statement will be false. And having the truth table allows you to understand what's going on fully, because this is all a possibility. So if somebody presents you with a truth table that describes this and the operator fully. All right. So we can do something similar with the or, but then already we have to be careful here because there are two types of ors. There's the inclusive or and an exclusive or. In English, uh, you have both types, okay? So, um, so let me give an example of an inclusive or. So let's say, to be admitted, you either have to have purchased a ticket in the ticket booth, or you had a coupon that you get by buying a cereal box or something, okay? And then if a person has either one of those, they get admitted to the concert, right? If a person has both for some reason, let's say the person didn't know that he or she had a coupon, bought the ticket, they can still be admitted. Nobody's going to kick somebody out because they don't have they have both, right? So in this case, it's an inclusive or, right? Now, however, there's some exclusive ors. So for example, uh, your I don't know if your parents ever told this to you, but they might have told you, eat your vegetables or go to your room, right? So what does that mean? It's either one of the two, right? You either eat your vegetables and you're fine, okay? Or you don't eat your vegetables and you should be going to your room, okay? Now, would it be possible that you eat your vegetable and then you still get sent to your room? Well, that's like a little not right with this statement. The statement says for eat your vegetables or go to your room to be true, you really want one of the two to be true, not both of them to be true, right? Yeah. Um, yeah. So you need to get 100 on your next math test, or you're kicked out. Okay. How that works, but let's say that. Okay. Now it would be totally unfair to that kid if he really did get 100 but still get kicked out, right? So that or would be an exclusive or, right? Uh, Now what I'm trying to point out is that um, because everyday English has two types of or, given the context, right? It's not so easy to just translate that directly to logic because we're doing math, and math, you can't have double meanings. You really need a single, well-defined meaning for things. So uh, what we're going to do is we're not going to be using exclusive or, but using inclusive or for mathematics. And here, when we write P or Q, this is really the inclusive or version of P or Q, okay? And there's a separate symbol for exclusive or, but there isn't any universally agreed upon symbol for this. So I've seen something like some people do P plus Q, some people do P star Q, like this. I've seen that. So there's some other flavors because exclusive or is less used. Um, People make up different symbols for it. Okay. All right. So since we just figured out that inclusive, this symbol means P or Q. Let's build the truth table for that. So PQ, P or Q, and true, 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 false, false, true, false, false. Okay. All All right, so true, we should be getting true. Because this is an inclusive OR. Both could be true and it's still true. If this was an exclusive OR, then this would be false. Okay. But this seems to be the one that's used in math more, so we just stick to that one. In any mathematical statement, when you see the word OR, you should think of it as inclusive OR. Okay. Yeah. Right. TF would mean
True.
FT true again. FF false. Okay. Now sometimes having a truth table allows you to see that two statements are equivalent, right? So I want you to look at the following. What I want to do is I want to show that these two, this statement is the same thing as this statement by showing that they evaluates the same truth value for every possible combination of P and Q. Now this twiddle before the P, that's not. So it's not P, not Q, but that's not universal. So in some textbooks, you're going to see not P written in this way. And so usually they write this or that. Okay. I'll stick to this one, but make sure that you understand sometimes textbooks use it this way, right? Okay, so we'll again write down all the possible truth table, true false combinations. Okay, and then not P would be just the opposite of all this. So TTFF, if you do a not, it'll be the opposite. Not Q would mean not T would be false, be true, be false, true. Now let's try to think about the OR statements. If you have two things connected with the OR, then you end up with true if you get true for at least one of them, right? So if you just look at here, only when they're both false, we know that it's going to be false. But when you have true in any one of these places, this is going to evaluate to true, right? Agreed? But then P and Q, true gives you a P and Q as true. So that's going to give you false. And then all of these will have the end evaluate to false, right? All of these will be evaluated to false, right? So we're going to write down this, which is equal to true. And now compare the two. You get FTTT, exactly the same. So now we have an equivalence which says that not P or not Q is equal to not of P and Q. Now you can also verify that if you do not P of and not Q, this has the same truth table as not of P or Q. And these rules have some commonality, which is that if you have a not operator outside and or, what you can do is you can distribute that not operator to each individual ones, and you flip the and to or to and. Is that good? And that has a name that's called De Morgan's law. And by calling these two as De Morgan's law, sometimes you can take some shortcuts to prove such and such identities. So you're going to see De Morgan's law appearing in several places in the homework. Okay, do you have any questions so far? Pretty straightforward, right? Okay. The way you can see why this is true, I said we don't care about examples, but let's do an example to see why this is true. So for example, P is age is less than 21, and Q is drinking. So if you're in a bar and you're drinking, right, and then you're over age 21, then you might get in trouble, right? Or the bar might get in trouble. Right? That's probably that's the letter is the case. Right? But as long as it's not that somebody is both under 21 and drinking, all is good. Okay. Some places lose their license, liquor license, because somebody was underage and drinking, right? Yeah. So this would be the rule. Okay? You want this. Okay? Now, is this same thing as not underage or not drinking? Makes sense, right? So for every person that you see in the bar, you might go ask, like, are you underage? Are you drinking? And if they're both true, then it's bad, right? So it better not be true, right? So you want this value to evaluate it to be true for every person, right? But here you're saying for every person, this person's either not under 21 or not drinking. Okay, then this is fine. Yeah.
So what is the things in the middle? If they're like upside down
or yeah. So this one is and.
Okay.
This you should really think of this as and.
And then the other one's or.
Yeah, and yeah, and then the opposite one is or. So not P or not Q, and not P and Q. So if you think of an example, you can kind of make sense out of this, that what you're writing down is true. Now, you can already see why this could be useful in coding, because sometimes you have to check for certain conditions, right? And here, look at how many operations you're doing to something. So you have to do a not operation, another not operation, and then or, right? How many operations? 3 operations. That's what's done, right? But over here, we have 1 operation and another, just 2 operations. So by rewriting this into here, you've saved the number of operations needed to do something. Now, when it becomes a time critical kind of, if some code needs to be really, really optimized, then knowing the equivalence that these two are the same thing can be really helpful, because instead of writing it like this, you can just write this. Okay? So P implies Q. P implies Q. And it's also known as if P, then Q. Let's talk about this one. P implies Q. And just to help with okay, so to help with this, oh yeah. So this is a similar situation as the or case. In the or we had inclusive or and exclusive or, right? So in the if, you also have two types. I would say inclusive if and exclusive if, but nobody says that. Rather, they say if and only if. So there's the everyday in everyday English, when you say if, there are two things, there are two cases. It could be just the if, or it could be if and only if. And again, we have to choose one, just one, and not the other for our logic. Okay. And to explain those two cases, here's a case. Uh, if you get 100 on your math exam, keep saying this, not to pressure you guys into the quiz that we are about to take, but if you get 100 on your math exam, I will buy you a bicycle. Okay, so that's like a if statement, right? Now let's say that the kid did get 100, okay, and then the dad bought a bicycle, right? All is fine, right? Okay, so P is 100 in math, and then Q is buy bicycle. Okay. Now, if this is true and that's true, then all is good. Right? The statement that Dad said is not a lie. Right? Okay. If this is false, no. If this is true but that's false, then Dad lied. Right? Do you agree? If the kid did get 100 in math, but then the family was really poor and couldn't afford a bicycle, sad story, but that means Dad had lied in his statement, right? Okay. What if the kid did not get 100 and Dad didn't buy the bicycle? Is this still a true statement? That's okay, right? If the kid didn't get the 100, so Dad said no bicycle for you, sorry, then the statement is true. Now, what's not so clear is this case. The kid did not get 100, but Dad bought a bicycle. Did he lie? What do you think?
Yeah.
Huh? Kind of, right? Because because the way we process English is like really, if you don't, if you get 100 in math, I'll buy you a bicycle. But then tacitly we assume that if not, no bicycle for you. That's the way that we understand that. Okay? And that's the case of when if is used for that. Okay? If you get 100 in math, and only if you get 100 in math, I'll buy a bicycle. Yeah? That's how it works. Okay? But going back to the other case is like you're at the gate of a concert, okay, EDM concert or something, okay, and then there's the guards like checking your tickets and stuff, right? Yeah, and the guard says if you have a ticket, then you're in, right? Now somebody came in, didn't have a ticket, he's out, that's fine, right? Somebody had a ticket, he's in, that's fine, right? Uh, if somebody had a ticket, but then the guard said, no, you can't come in, then the guard lied, right? The problem is what happens if somebody didn't have a ticket and was let in? Well, it depends on the context. Maybe this person had not the ticket, but some other coupon that allowed him to go in, right? So when when the guard says, if you have a ticket, you can come in. That doesn't mean that you can't come in if you don't have a ticket. I mean, uh, if you're working for the company, you can still go in, right, without the ticket, right? So maybe this is not a good analogy. Another analogy is something like this. A college says we will admit you if you get 1,500 or above in SAT, right? But then there are plenty of people who gets admitted without the 1,500 because like this person's phenomenal in sports or they're doing something else, right? They have some extracurricular activities that was phenomenal. So in those cases, making a statement that if you do this, then we'll do something is not really presupposing what happens if you don't do it. Okay? So in English, there are two different kinds of if. Would you accept what I just said? Do you agree that in English there are two kinds of ifs? All right. And then when it comes to logic, we don't use this one. This one will be really written as if and only if. It's a separate notation. If and only if will be written like this, arrows going both ways. All right. And then this one, when you see an arrow only one way, then it will only be talking about the one kind of if, which doesn't say anything about what happens if P is false. Right. So let me clarify what I just said by building a truth table. And maybe after seeing the truth table, you'll have full understanding of what's going on here. Okay? So, true, 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 false, false, true, false, false. Okay, well, of course, true, true means the original statement was true. Okay? The promise was fulfilled. If my part of the bargain was done, but the other guy failed to meet the bargain, then the statement that was given to you was false. Right? But if my part of the bargain is false, then because we are working with this first flavor of if, we don't really care about the outcome. Outcome can be either true or false. In either case, the original statement is still true. Okay. Yeah. On the other hand, if you have if and only if, then this is still the same, but if my part of the bargain is false and the other guy has the truth, that's not good. That makes the original statement as false. Okay? Yeah. False, false would be true. So in other words, this is like saying that P if and only if Q is when P and Q have exactly the same truth values. Okay? If they have different truth values, then P if and only if will evaluate to false. Is that okay? Yeah. This is the most confusing part because many people don't distinguish between these two types of ifs, and they think that the definition is not right, but what we're just doing is like identifying two different flavors of the language. You know, English, the everyday words are not exact enough to be used for computation. And we use logic to compute things, so therefore it's very important we stick to only one meaning of things. Okay. Build a truth table or the truth table for not P or Q. Okay. What do you see? Try this out. So it's going to be PQ, true, 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 false, false, true, false, false. Okay. P, not P or Q. Well, first of all, not P is false. False or true gives you?
True.
True. Not P is false. False or false gives you?
False.
False. Yeah. Not P is true. Well, if you have true, then or will always give you true, right? So if you have one thing that's true, that's true. Okay. So false, not P would be, not false would be true, true or F will be true. Okay, what do you see?
There's only one false.
Huh?
There's only one false.
Only one 12? What do you mean?
False.
One false, okay. Like
Oh,
P implies Q.
yeah,
this one, right?
yeah.
So, as I said, if we have two symbols giving you the same truth value, then they're treated as equal. And so, what we've just finished showing is that P implies Q has the same truth value as not P or Q. Okay? Now this gives you, for one, a way to rephrase something with another one. Okay? So let's say you can be in our basketball team only if you're 6 feet or higher. Okay, so that can be phrased like this. If height is 6 feet or higher, okay, then allowed in basketball team. This is slightly different. Sorry. This is like let's say it's a high school team, not many 12 players there, and let's say the coach says, if anyone's more than 6 feet, he's in, right? That's what he's saying. Okay, yeah. But it could be that there's some guards that are very skillful, right? Let's say somebody who can like shoot 3-pointers really well, right? Yeah. And in that case, he's still admitted for a different reason. Okay, so that's what this is saying. Right? Remember, this is not an exclusive type of if. This means that if this condition is met, then something can happen, right? Okay. So now let's try to see. Now let's try to see what this other one is saying. H. So if this is P and this is Q, let's say H less than 6 or allowed in basketball. Okay. Okay. So what does that mean? That means for any student in that high school, you can say the following: that student is. It could be that that student is less than 6 feet tall, or it could be that that student is allowed in basketball. Okay. And we're saying that these are the two. These two statements are saying the same thing. Okay. The first one is saying, oh, if anyone's more than 6 or more, yeah, he's welcome. Right? The second one is saying, for every student in this high school, we can say that the following statement is true. That person is less than 6 feet or he's allowed to be in the basketball team. Do you see that they have the same statement? No? For every student, the following is true. It could be that that person is less than 6, okay? Or that person's accepted into the basketball team. True, right? Because if this is not true, then that person is 6 or higher, taller, 6 or taller, so he must be allowed into the basketball team. All right? Okay. So you can see that this statement allows you to rephrase an if statement into another statement, doesn't use the if statement. But there's another use for this. Knowing this allows one to take the opposite. So here's a observation here. Suppose you want to make the opposite statement, not the opposite, the opposite has a different meaning, sorry. Suppose you want to negate a if-then statement, okay? So let's say some guy said, well, you said this before, but that was a lie, right? You want to refute this, okay? You want to make a negation of that statement, okay? Now, we don't know how to do that, but if you rewrite this as not P or Q, then we learned something called De Morgan's law, right? What's the De Morgan's law? De Morgan's law says I can distribute the not to each individual parts and you flip this, right? So if I do not of P and you flip this upside down and then not of Q, then since not of P is just P, and you have this. Okay? Now, in this context, what does that mean? That means there was a student who was 6 feet or taller, but then he wasn't allowed into the basketball team. So that one student can be a counterexample to the coach's statement that was made earlier in the semester, right? Earlier in the year. Okay, the coach gathers in. Oh, we need taller players in this team. So you just tell your friends, anyone who's 6 feet or taller, they're welcome, right? But then later on, then some guy wanted to go in, and coach didn't like him, and then this happened, right? And then that makes the previous statement a lie, okay, a false statement, right? So you can kind of see how to make a negation of an if-then statement.